Buddy, how's it going?
I can't say hi normally.
Yeah,
Excited for Bright.
that makes sense.
Are we gonna be doing it much tomorrow?
Yup. It's like a regular day of school, man.
Well, it's like half the time. So I know some teachers are like, we don't do much, and some teachers are
Hey, senior skip day. Rumor has it too.
Haven't you had 3 of those already?
Haven't they all failed?
Well, I haven't got that.
What is the official
Marcus
day?
was like, can I go to IT, please? My computer's like not turning on.
Okay.
Yeah, I'm always the only senior skip on that day.
All right. Hi, everybody. So today we're going to look at 15.2. Before we dive into that, though, let's look at an example from 15.1. So this is one of the homework problems assigned in the 15.1 homework set. So this reads, the number of grams of carbon-14, denoted C, present in a certain substance after T years, that's probably supposed to be years, is given by C of T equals yada, yada, yada.
Thank you.
What is the initial amount of carbon-14 present? So that's looking, because it asks for the amount of carbon-14. We're looking for a value for C. To find the value for C, we need to put in a value for T. So what value of T would initial mean? T equals 0. So I'm just going to compute C of 0. Probably the easiest way to do that is to just do this on my calculator, because it appears that I have a bunch of other stuff to do on my calculator. I'm going to do it this way and plug it into my y equals negative 301216. 1231216x. So I'm going to type it into the y1, and then I'm just going to do y1 of 0 to get 20 grams. Part B then says how much is left after 10,400 years. So what are we going to do here? Just going to plug in 10,400 in for T. So I have 5.65 grams. Is everybody okay on that? Okay. Part C then says, when will the amount remaining be 10 grams? So here we're asking to solve for C of T is equal to 10. So our answer needs to be a value for T, which represents some amount of years. So to solve this equation, what I'll do is I'll go to my calculator, and I'm going to graph my equation for C and y equals 10, and search for the intersection. Now, to find that intersection, though, when I graph this, I have to make sure I'm choosing a window appropriately. So let's talk about how to do that. The x value is representing time. What's the smallest value that I could have for time? 0, right? Because you can't have negative time. And then if I look at part B, I saw that after 10,000 years, we got like 5.65 grams. So certainly between starting at 0 years when we had 20 and 10,000 years, I would have had to cross 10 somewhere in there, right? So 10,000 seems like a good value for my X max. And maybe we'll go by thousands. Okay. Now the Y is representing the amount of stuff I have left. What's the least amount of stuff I could have? 0, right? You can't have negative stuff. And how much stuff did I start with? Was the most I could have had? 20, right? Because we start at 20 and we're losing. And maybe we'll go by 2s. So that looks pretty good. I've selected a window that should make sense for my situation. Now I'm going to hit graph. So the blue curve is my value, or is my equation for C of t. The red curve is the line, y equals 10. And I'm searching for the intersection of those. To find that with my calculator, I'll press second and the trace command. Select intersect. Press enter 3 times since I just have 2 lines and 1 intersection. It doesn't really matter. And I find that after 5,700 years, I should be about 10 remaining. Any questions on what I've done here? So this is just a review of 15.1. I chose this problem to look at because many of the calculator techniques I use to do this problem, I'm going to be recycling to use in 15.2. So it was a nice little review of those calculator skills before we dive into the new stuff. Everybody ready? Okay, here we go. Okay, so in section 15.2, we're going to talk about exponential and logistic modeling. So this means if we're talking about modeling, it means that we're going to be writing our equation, right? So we're going to start by giving you the general form for the exponential population model. Which looks like this. Okay, so P of t is the population at some time t. P naught is the initial population, i.e. the population at t equals 0. R is the percent rate of change. And t is just time. Okay. So what we're going to look at now is we're going to look at going from an equation to getting these coefficients back out. So ideally, can I pull out P naught and R from an equation. Everybody's okay? So let's look at an example. So we're going to be asking, what are the values for P naught and R? And then is this going to be population growth, or is this going to be exponential growth or decay? Okay. So first thing, if I look at my exponential population model, I should be able to match up the parts with this, right? Is everybody okay with how the parts of the equation match up with our model? So we can see right away that P naught is equal to what number? 12,587. Everybody's okay there? That should be really easy. I can just read it off the equation. R, though, will be a little bit more complicated because I see that R is actually, or the 1 plus R over 100 is actually equal to the 1.0384. Yeah. So we'll just solve this algebraically now. So I subtract 1 from both sides. And then we'll multiply both sides by 100. And we get that R is 3.84%. And I should probably put a percent sign at the end there. Is everybody okay with how I did that? Pretty easy. And since R is greater than 0, we know this is growth. So far, so good. How would I know it's decay?
If it was less than 0.
If R was negative. Yeah, wonderful. How do you guys feel on this? Do you need to see another example, or are we happy with what we did here? Should feel relatively straightforward. Alex?
I understand how much you plugged it in, but where do you get 12 out?
I mean, this is the problem,
Oh,
and we're just pulling the values from it. So you're given the equation. I just wrote the other thing underneath it so you could see how I'm pulling the values. Does that feel okay?
yeah.
Okay. So again, like not doing anything sneaky here, right? We're just literally like, okay, the equation looks like this. So this part is this and this part is that. That's all there is. All right. Now let's look at going from a description to an equation, right? Here we went the reverse, went from the equation to a description. Okay. So here it says determine the population model. Oh, since we want an exponent or a population model, I'm going to use my population equation. I'm just going to be filling in values for it. Okay. It says with an initial population of 15. What does that mean? What initial population of 15 tells us what? Tells us P naught is equal to 15. And then we have that it says increasing at a constant rate of 6%. What is that telling us? R is positive 6. Why did I emphasize the positive? Yeah. Increasing says R is greater than 0. If it said decreasing at a constant rate of 6, it would mean that R would be negative 6. Everybody's okay there? And if I combine, or I do a little simplifying, 6 over 100 is 0.06, and if I add 1 to that, 1.06, and I'm going to clarify that T is in years. Yes, sir. Sure.
So for this one, you don't actually have to like solve anything. You just have to make.
It just says it wants the model. That means our answer is an equation. Yep. As we move further on, it'll ask us, like, give us the information, then ask us something to do with the model. But for right now, we're just writing the model. Everybody's okay? All right. Okay. So our next example says determine the population model with an initial population of 15, increasing at a rate of 6% every 6 months. This should sound almost identical to the previous example, right? What's the only difference between this example and the previous example?
That gives you a specific time.
Could you do 2 over 2?
Okay. We'll get there, but you're right on. Everybody notice that that's the only difference between this example and the previous one, right? So our values for P naught and R are still going to be exactly the same. Now we have a choice, right? In the previous problem, we chose that that T was in years, right? Here now we should make a similar distinction. Now we probably have 3 different options the way that we could do this. We could choose T to be in years again, or we could choose T to be in months, might make sense. Or if you wanted to be a little more obtuse, maybe you could say T in
Weeks.
6-month intervals. Okay? And depending on what unit we want to choose for T, we'll alter this equation slightly to represent that. Everybody's okay with that? Now, probably most naturally, we'd want to pick T in years. If I did that, how many how many times should that 6% increase happen inside of 1 year?
No, oh yeah, right, sorry.
2, right? Why 2? Because in 1 year, 6 months happens twice. Everybody okay with that? What if instead we wanted to write this in terms with, I'm sorry, where t is in months? Nope. So how much of the 6% happens in 1 month? 1/6. So you'd have t over 6. Is that okay? Or maybe you would choose to say t is in 6-month intervals.
Just see.
And so that would be just t. Now, all of these are equally correct on a test or quiz. If it doesn't tell you the unit that t needs to be in, you're free to do it any way you like. But what I will need from you is you got to give me this piece when you write your equation. Okay? I will count anything that's correct as correct, provided you tell me the unit that you're writing your equation in. Deal? So I'll accept all answers, but you got to tell me what unit your answer is in for me to count it as fully correct. Okay. Let's do another example here where we ask you to write the model and then answer some question based on your model. Okay, so this one says, suppose that a colony of 120 bacteria is put into a petri dish, and the culture doubles every 3 hours. Predict how long it would take for there to be 400,000 bacteria. Everybody clear that we're talking about a population here, right? So to describe this, we're going to use our population model. Everybody's good here? So the first part of my problem is going to be asking to write your population model. And then the second half of the problem is going to be solving that population model. Thanks, Anthony.
Thanks,
You too. Everybody's okay? Okay. So let's start by writing our model. What is our initial population? 120. What is our value for R? 100 is correct. How'd you get that, Mark?
Doubles.
Yeah, why does doubles mean 100?
Because 100% of something is its full thing. So if you're doubling something, you're taking 100% of that and adding it on to what you already have.
Yeah, so if you say that something costs $1 and you increase its price 100%, you're adding $1 more to it, making the price $2, which has doubled the price. Does everybody feel okay as to why doubles means 100% rate change? Okay. And now we're going to pick a unit for t. What unit of t would we like to pick here?
3 hours.
Hours sounds fine to me. Okay. How much of the doubling happens in 1 hour?
1/3 of it.
1/3 of the double. So we'll write t over 3. Or you could write 1/3 times t if you want, but like, it's extra symbols, you know, like, just give me that t over 3. Is everybody okay? Then what it asks is, okay, here's a value for p of t. And we want to solve for t. Everybody okay there? To do this solving, I'm going to do this just like we did in the homework problem from 15.1 that we looked at the very beginning. I'm going to graph and find intersection. Okay? So I have y equals 120, and then 1 plus 100 over 100 is just 2. And the y needs to be 400,000. Is everybody okay with what I've typed into my calculator? Now I need to set a window. This is often going to be the hardest part. So I don't have a real good idea of how long it's going to take. Maybe I just kind of thinking through in my head. So after 3 hours, I should go from 120 to 240. 6 hours, 240 to 480. 9 hours, 480 to 960. And we see this is going to be a while, right? I'm just going to take a guess and maybe say 100 hours or something. I mean, doubling's pretty fast, but let's just say 100. I don't really know. The minimum amount of, now the y is representing bacteria, right? What's the minimum amount of bacteria I have? 120. What's the maximum that I care about?
400,000.
400,000. Now, I want to see a little, I'm not going to type 120 in because 0 is close enough. And I'd like to see a little bit above the 400,000 so I can make sure I know when it crosses. So I'm going to pick 500,000 here just to give myself a nice picture. And then we'll go up by 100,000s and hope that I picked a big enough X max to where I can see the intersection.
500,000 going up by 2 each time.
Be a lot of tick marks.
Yeah.
You just get a solid line.
Just a few.
So there's my curve and there's, okay. We see the intersection, it's right there, nice and clear. So second trace, intersect command, enter, 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 and there we go. 35.1 hours.
What are those little lines now?
I must have something, I don't know what those are doing. I don't know why that popped up, but I'm not sure what that was from. It must be some weird mode. I use this thing for all these other classes. I probably had something else going on in like from AP Calculus or something. I don't really know.
Trying to make sure like it was.
No, I don't know what it was doing there, to be honest with you. Is there something hiding down here? None of the plots are on. I don't really know why it's giving me that extra stuff down there. Looked like part of a a slope field graphing, but I don't know why it would be doing that. So anyway, is everybody okay with how I solved for the t? Now, notice that if instead I had written this like as p of t equals 120, 1 plus 100 over 100 to the t, where t is in 3-hour intervals, I'm going to get a different answer, right? So if I change this and I do this, I graph again, and I find the intersection, I get 11.7. But notice that if I take 11.7 and multiply it by 3, guess what I'm going to get? That same 35.1 that I got before. So these two answers are equivalent. They're just in different units. So here I would need to be careful and say 11.7 3-hour intervals. Or I could take that answer and like multiply it by 3 and write it as just hours.
But as long as you put the t's in 3-hour intervals, you don't have to.
Unless the question specifically asks for the number of hours. This said how long.
Yeah.
So you're free to use whatever unit you'd like. It just would be a question of what is the question really asking for. But here, either would be okay. And notice that even if I chose to use 3-hour intervals and I realized afterwards, oh, crud, the question asks for hours, I just multiply my answer by 3. I don't have to redo the problem or anything. It's fine.
And then if you accidentally did it in hours and it asked for it, you just
Divide by 3, exactly. Yeah. So once you've done it, it's easy, usually pretty easy to change the unit after the fact if you realize, oh, I used the wrong unit here. I should have done blah, 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 blah. Everything feeling okay so far, folks? Okay. Another specific application of the population model is, go ahead, is radioactive decay. Have you guys talked about radioactive decay in your science class before? Okay. So here's the idea. So you have some radioactive substance, and that substance is going to emit radiation. That radiation will take the form of some elementary subatomic particles, protons, neutrons, electrons, whatever. As that substance emits radiation, it loses mass because those particles, those protons, neutrons, electrons, all weigh something. So it loses mass, and if it's losing protons, it becomes a new element. If it's just losing neutrons or electrons, it's going to become a new isotope. But the time it takes to lose half of its mass, we call a half-life.
Is this the part of class where you're going to make me regret taking physics instead of chem?
Nope. Because all this matters to you is when you hear the word half-life, you just think R is negative 50%. Everybody's okay? That's the key for us. Half-life means that R is negative 50%. So I just want to give you a brief description of what's going on, just so as much as to like, okay, I guess I understand what's happening. The key here, though, is when I hear half-life, I just know that R is negative 50. Let's do a quick example. Yes, of course. Okay. So here it says, suppose the half-life, and again, I hear half-life. So again, as soon as I see that R is negative 50% of a certain radioactive substance is 35 days. You have 10 grams of the substance initially. Find the time it would take for there to be only 1 gram remaining. So it says we have 10 grams initially, so that's my P naught. It says half-life, so that means R is negative 50. Now we need to decide what unit T we want to use T in. Okay, that makes sense to me. So how much of a half-life do we have happen in 1 day? 1/35. So we'll have T over 35. Everybody feel good? So that's like the first half of the question. And in the second half, we're just going to be solving P of T is equal to 1. Everybody feel good? Okay. Let's get that into our calculator. We're going to do it again the same way. I'm going to simplify that piece in the parentheses. 1 plus negative 50 over 100 is 0.5 or a half. What's that? 1 plus negative 50 over 100 is 1 minus a half.
So should it be x over 35?
Yes, it should be x over 35. That is true. That's okay. As long as you're catching my boo-boos, that's great. All right, now let's set a window. So I'm going to just kind of think through this real quick. So it takes 35 days to go from 0 to 5, 70 days to go from 5 to 2.5, 105 days to go from 2.5 to 1.5, and by 140 days, I'll have gone from 1.25 to less than 1. Everybody good with that? So I'll make my X max 150 because it's a round number. I'm surely catch it by then. The Y's, the minimum Y I can have is 0, again, because stuff is decaying. The most amount of stuff I'll ever have is the start. That's that 10 grams. And I think just going by 1 seems good. All right, we'll hit the graph. There's my curve. I see an intersection. Second trace, intersect command, enter, enter, enter. And I have 116.3 days is my answer. And again, you could write this answer in half-lives or whatever if you chose to do it that way. We did that example once of showing how to convert back and forth and why it doesn't really matter as long as your unit is there, the way you give your answer. So I'm not going to do it again.
Would you, if you did it in half-lives, would you times by 35?
You would divide that by 35 to get the number of half-lives. If you did the problem in half-lives, you'd multiply by 35 to get days. Yeah. And again, like, it doesn't really matter unless the question asks for a specific unit, right? If it asked, find the number of days it would take, then your answer needs to be in days. If you gave me like, oh, that's like, 3.6 half-lives, I've been like, ooh, not full points because we asked for days, even if it's the correct number of half-lives. Yes, of course, yeah. If it's like 3 points, it'd be like 2.5 out of 3 or something, or 2 out of 3. Because you did most of the hard work correct. You just goobered that answer, how you wrote your answer. All right, one more example, and we're going to be done for today. How's that sound to you guys? All right. So we're going to give you guys a logistic model here. You will never be asked in this class to write your own logistic model. Rather, you'll just be given one in the problem and be asked to use it to do stuff.
I love the randomness of the examples. Start a fun petting zoo.
Yeah. This model only has one L. All right, you start a bunny petting zoo. You determine that the population of bunnies on your farm can be modeled by the equation B of t equals yada, 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 where t is in years. And you're asked how many bunnies do you have initially? So the key is that initially means that t equals 0. So we're just computing b of 0.
So you said like in a problem like this, we'll always be given like.
You would not be expected to write your own logistic model. Yep. So just like the example at the very beginning of class, I'm going to, because I'm being asked to do a couple of things here, I'm going to type this in to the y equals and use this to do my solving rather than do it directly. So I'm just going to do y1 of 0. So that tells me I had 8 cute little bunnies at the start. Part B asks, what is the maximum sustainable population? Now, if you remember from 15.1, a logistic equation, which is something that looks like this, has 2 horizontal asymptotes. One of them is at y equals 0. And the other one is y equals the numerator. So that's going to be considered my maximal sustainable population. Is whatever that numerator is the maximum value. Everybody okay there? And then part C asks, how long will it take to get to 500 bunnies? So here I want to solve b of t equal to 500. And give my answer in years since my equation was in years. So I'm going to go to my calculator, type in 500 for y2, set myself a window. I don't know how long this is going to take really, but there's bunnies are known for reproducing slowly or quickly. Quickly, right? So I don't know how long this is going to take, but I would guess by like maybe 20 years, I'm going to have just like a lot of rabbits. I'm just guessing. I don't know. I might have to re-extend that, but I might get away with that. I don't know. I'll go by 2s, and then my Y-mins are just going to be the horizontal asymptotes. So like 0 and 800. And going by hundreds there seems appropriate. And let's hit graph and see what we got. Oof, right in the middle. Nailed it. So I'll do second trace, intersect command, enter, enter, enter. And I have 10.2 years. And we're done. How do you guys feel on this section? Should have felt okay, right? The calculator's handling most of it. We just have to kind of write the equation, use the calculator to handle everything else. So as long as you feel good on the calculator piece, it's not too bad.
I do have a question. How come you have to do the intersection thing? How come you can't just do what you did with like the initial population variables? Like you did like the Y1.
So I can plug in, because here in parts A and B, we're looking for B of t, and we're given a t. In part C, we are given the B of t, and we're looking for the t. So the function doesn't work in that way, where if we're given an x, it's really easy to find the y. You just plug the x in. If you're given the y to find the x, you have to solve. And we haven't discussed algebraically what you would need to do to solve for a exponential logistic equation. No, it's not stupid, man. I'm sure somebody else was thinking it. You can say, oh, I knew the answer to that after you asked the questions, like I should have known better. That's fine, but like not a dumb question. I'm sure other people were thinking the same thing. Because that's happened a couple of times now where it's like I have to graph. In general, when you're trying to find the independent variable, that's going to be solved by graphing. If you're looking for the dependent variable, that you can just plug the independent in. Pops out. So your assignment for your PS or problem set 2 for chapter 15, due this Sunday, is 17 through 36. Mostly just using your write the equations and use your calculator, and there's not a whole lot complicated going on here. Yes, sir. Sure. And I'm gonna stop talking and let you guys take this last half hour or so to make a dent in that.